Okay, good afternoon. This is the second lecture on robust artificial intelligence. We have finished one lecture on this topic, giving examples of where today's deep learning AI is brittle. We saw examples of point intelligence, pointistic intelligence, and narrow intelligence, where the AI breaks down unexpectedly. And we saw some examples of the performance of chatbots such as Alexa and as well as GPT-2, how they end up doing extremely well, and they look very impressive on the one hand, and on the other hand, they miss out on any kind of reasoning and so on. So today's lecture is going to take that concept further and argue that that robust artificial intelligence needs a cognitive model. Right? We'll talk about what is this cognitive model, and that is what is missing. So today's deep learning performs very well because it discovers correlations in the data. It says, okay, if you see something, and it means that it's correlated with something else. And so it discovers these very unusual correlations and so on. And based on statistical correlations, it can perform extremely impressively. But what is missing is an understanding of the concept underlying things. And so what is needed, and we'll give some more examples of the lack of understanding of today's artificial intelligence based on deep learning, and look at this idea of developing a hybrid artificial intelligence system, which is a combination of neural networks, that's where the neuro comes in from, and symbolic methods. And some kind of a hybrid model is what is called for. Okay, let's begin then. All right, the topics today, we begin by talking about memorization versus reasoning. The argument here is a deep learning does memorization. Of course, one could immediately jump back and say, hey, wait a minute, deep learning does a lot of regularization. It's not just pure memorization. But still, even with regularization, it is looking for clouds of points where there's some kind of correlations that exist. So we are kind of being critical about it and calling it as memorization. And we'll talk about reasoning is not memorization, but based on your observations, can you do some reasoning rather than simply memorize what it should be? So we'll talk about that. Then we will look at a famous play of William Shakespeare called Romeo and Juliet. This was taken up as an example in a project of old AI, right? It's called GOFAI. GOFAI stands for Good Old-Fashioned Artificial Intelligence. And Psyc is a project of good old-fashioned artificial intelligence. And we will talk about the kind of reasoning in Romeo and Juliet. And then we'll talk about what cognitive models. And the theme here is that the cognitive models are what is needed. And then a particular project that came out last year called Meena. This was put out by Google, saying that this chatbot is better than any other chatbot of that time. This is just 1 year old, 2020, January or February, about a year ago. And then we look at some cases and say even Meena does not have an understanding when it's chatting with human beings. And then we go on to talk about a conjecture for robust intelligence. What is needed for robust intelligence? Here we argue that you need a cognitive model, and a cognitive model is essential for robust. That's the conjecture. And then we'll talk about the role of abstraction in human intelligence, that an essential attribute of human intelligence is the ability to abstract stories from specific situations. And finally, the proposal for a hybrid model, which is basically a neurosymbolic architecture. We're still at the motivation stage, arguing why another paradigm is needed in AI. Deep learning is well and good, achieved a lot, but where do we go from here? Okay, memorization versus reasoning. All right. So we say that deep learning artificial intelligence copes with complexity by trying to memorize the probability density function for the entire world at the cost of needing more data. So this says, okay, we're going to throw in all the data into the brain. I guess that's the picture on the top right. And that's memorization. And then the graph at the bottom is all kinds of probability density functions, saying the entire world on whatever be the attributes and so on. And how do you construct probability density functions is by feeding it data. And this strategy, given the exponential complexity of the world, so that is, how can you keep on adding more stuff and creating more probability density functions? It is all exponential in nature. Things keep changing. It's a strategy that is unlikely to work. So we argue that memorization is not the way to go. Reasoning offers an alternative. So this is arguing here that instead of memorizing everything or interpolating between near neighbors that you might have previously encountered, so memorization, we're saying it is not exactly what you had seen before, but something close by. Near that, you draw inferences. We're saying inference is important. Instead of memorizing that Plato, Aristotle, Euripides, look at this this bus we have of Sophocles, Euripides, Aristophanes, Plato, Aristotle, Socrates. Some of them were dramatists, and some of them are philosophers, and some of them were students of each other, right? Plato was a student of Socrates, and Aristotle was a student of Plato. And they kind of laid out all the philosophy, Western philosophy of arguing out things back and forth. And that is how one develops knowledge. Anyway, here we're talking about, instead of memorizing that Plato, Aristotle, and Euripides, and each of the other billions of other individuals preceding us were all mortal. All right, we can have a deep learning system that says, Socrates is mortal, right? Socrates was a man, all men are mortal, so on. So if we just keep giving these examples, we are not necessarily learning that all men are mortal, but if you are able to learn that all men are mortal, then you learn a general truth, that all humans are mortal, and apply that general truth to specific instances of that category as needed, right? So this says, don't memorize that this one is mortal, that one is mortal. Just have the general concept. So symbol manipulation holds promise. Neural nets such as transformers are too unreliable to make for sound reasoners. They may work some of the time, but not robustly. And symbol manipulation offers at least the promise of heading the right direction, provided that sufficient knowledge is available. These diagrams here illustrate this idea of attention and transformer models. In the lower one, we show a pathway from encoder to decoder. Encoder takes, let's say, an English sentence as input, and we develop in between a context vector, which is then passed on to the decoder, which converts it into German. So the context vector is capturing all the context of all the previous text that has been encountered. And that whole thing was converted into a transformer model. And it was not a recurrent neural network. It is something based on multi-head attention, it is called, but essentially it is remembering all the previous information in the form of vectors. And this is the idea of transformers, completely based on neural networks. The argument here is such transformers are too unreliable to make for sound reasoners. Anyone who played around with Alexa or other chatbots will know that while the text is very coherent and it creates perfectly created sentences, sometimes it misses out on simple logic. Okay, let's look at the reasoning in a symbolic reasoning system called the Psyc Project. And they took an example of Romeo and Juliet. It's a famous Shakespearean play. And the Psyc Project, this is a diagram of the Psyc Project. What does the Psyc Project involve? The best case for reasoning engines, inference that Psyc, a symbolic system, performs in optimal circumstances. It's got a knowledge base, it's got an inference engine, it's got an applications module here, and some kind of a knowledge graph type of relationship here. So all of these together is the Psyc system. And what is the kind of reasoning that the Psych system could do with Romeo and Juliet? So these three diagrams are samples of story relevant knowledge. The first one is the plot summary, a section of the plot summary. Romeo and Juliet has, of course, it's a reasonable sized play. And this is about towards the ending of the play is the plot summary, as could be prepared for Wikipedia. Okay, let's read along so that we can follow what's going on here. It says Juliet visits Friar Lawrence for help, avoiding being forced by her father to marry Paris. And he offers her a potion that will put her to a death-like coma for hours. The friar promises to send a messenger to inform Romeo of the plan so that he can rejoin her when she awakens. She takes the drug, and when discovered apparently dead, she is laid in the family crypt. The messenger, however, does not reach Romeo, and instead Romeo learns of Juliet's apparent death. Heartbroken, Romeo buys poison from an apothecary and goes to the Capulet crypt. Believing Juliet to be dead, he drinks the poison. Juliet then awakens and, discovering that Romeo is dead, stabs herself with his dagger and joins him in death. So there is some ambiguity at the end of Romeo and Juliet, whether it ends in such a tragedy. But anyway, here are some points. This one is slightly different from that ending. Some points. Time T0, just before Act 4 starts. This is Act 4 of the play. T1A, at the start of Juliet's visit with Friar Lawrence. And T1B, the end of that visit. So this is the time frame here, some time points. T2 is what the friar and Juliet both believe about T4 and T5. And T3 is Juliet drinks the fiend death poison. T3B, Juliet's body is discovered and taken to the crypt. T4 is Romeo hears from the friar's messenger about the planned trickery. And T5 is Romeo hears from someone else that Juliet has died. And T6 is Romeo goes to the crypt and finds Juliet's inert body. T7 is Juliet awakens from her feigning of death. T8, this is a different ending. Romeo and Juliet secretly flee Verona. All right, so in this case, I suppose in T8, she doesn't die. Anyway, so these are the kinds of time points that could be associated with the plot summary. Some statements that are true at T0. Lord Capulet wants and expects Juliet in Paris to marry. Juliet knows that Lord Capulet wants and expects Juliet in Paris to marry. Right? So first is the Lord Capulet wants and expects Juliet to marry, and Juliet knows that. And then Romeo believes that Juliet is alive. And Romeo, Juliet, and Friar do not want Juliet to marry Paris. All three of them know that all three of them do not want that to happen. Anyway, there is all this kind of complicated plot issues to understand Romeo and Juliet. So you can regard knowing all of this, some story relevant knowledge. It's a cognitive model in that it is an internal distillation of a complex scenario, and it is rich in that it is filled with subtle information, but what particular protagonists do and know and intend and expect at particular time points. So it's kind of, so this has been done manually. They're saying, here is the plot summary, here are the time points, here are some statements that are true, and so on. So what about, we want to make some inferences after looking at this. That's where we're going to be heading towards. But it also requires some common sense and a complex inference mechanism. What are some common sense things? Rich common sense knowledge. Of course, if a person were dead, they would not have to marry anyone, all right? That is common sense knowledge. Of course, a person often asks another for help accomplishing something that they both want. Of course, if someone drinks an instantly fatal dose of poison, they immediately die. Of course, if a trusted friend of yours tells you something and you don't have a better reason not to believe it, then you're very likely to believe what they say. Of course, when someone newsworthy is believed to be dead, news of their death will spread quickly. The scale and speed depend on the information technology available and the dead person's level of fame. In particular, in a small medieval European town, the news of a local noble's demise would spread by word of mouth throughout that town over a period of hours, but in less than 24 hours. This is all common sense knowledge. And so what do we want to say about it? Some bits of knowledge might be represented explicitly. Example, consequence of drinking a poison might be instant death. Some derived online from more general facts. If a person were dead, they would not have to marry anyone, might be derived from observation that obligations apply only to living people. So some are explicitly stored in the common sense knowledge, other ones is derived. And then here is a sample inference. When she takes the feigned death potion, does Juliet believe Romeo will believe she is alive during the time she is in suspension? Right. And so does Juliet believe that she's alive at the time of the suspension? And the answer to that is yes. That's why, Juliet decided to do it. She thinks Romeo will know. If at time T1, the agent's model of a subject's belief, at time T2 includes the proposition that the agent believes T1, the subject believes the proposition T2, so on. And these are all some kind of inference. These are all drawn from a combination of the story, the plot summary, the time points of what the story is saying, and some statements that are true, as well as a rich common sense knowledge. One could make some inferences from that. Just like someone asking a question about the story after you've seen the play. Payoff in having such a broad fund of knowledge comes in the sophistication of the inferences that can be drawn. So this is the part here. And in their level of interpretability, both of which are in a completely different level from anything thus far produced via deep learning. So the argument that's being made here is the kind of story lines and the common sense knowledge driving sample inference here is much more sophisticated than anything deep learning would do. So observation, this is the kind of thing that Psyc is attributed to, the Psyc Symbolic Reasoning Project. The approach needs structured representations, operations over variables, and records for individuals. And what it shows is the value of cognitive models. We'll talk a little bit more about it. Knowledge about biology, right? So what people are thinking and so on, cognitive models, knowledge about biology, that if you take a potion, you can die. Theory of mind, issues like that come into play, but relies on hand translation of Romeo and Juliet into formal logic. The slide we saw where Romeo and Juliet, the Wikipedia plot summary was translated into formal logical statements. A system generating such representations automatically and reason comparably would be a breakthrough. This is not as if the psych does that. If you fed it the logical statements of Romeo and Juliet, it is able to draw inferences. Reasoning is not the bottleneck towards robust AI. Bottleneck is in having the right information accessible in the context of world inference. Another point, major point that's being made here, which sets some of the directions for our seminar, is that uncertainty is not modeled in psych. Even in psych's reasoning, there is much room for improvement. Its representations, higher order logic, cannot represent uncertainty and reason over distributions. So psych cannot reason over distributions. Well, a famous philosopher, Bertrand Russell, had to say, all human knowledge is uncertain, inexact, and partial. So if you have a logical system, then that can only take you so far because a lot of the knowledge is uncertain. This is the kind of thing that probabilistic artificial intelligence addresses, which is using probabilistic graphical models and so on, where there is uncertainty. How do you reason? So reasoning and knowledge are essential. An AI that can't understand a plot summary of Romeo and Juliet is not likely to be competent in the complexity of the real world. So you need an AI. We're just saying, supposing we just took Romeo and Juliet and fed it to GPT-2, which is able to digest large volumes of text, right? And you're going to be asking some questions. Did Juliet believe that Romeo will know that she's not dead? It has to say yes, right? Can it do that? An AI that can reason about the motivations of interacting humans as complex events as they unfold over time is a fighting chance. So an AI that can reason about the motivations of interacting humans, what was he thinking? What was she thinking? So on, right? Reasoning and knowledge need to be first-class citizens if we are to move forward. So let's see, we can say something about cognitive models, which we argue that it is essential for robust AI. Cognitive models are knowledge that accumulates over time. So we accumulate knowledge all the time. What we learn about a friend in the course of a conversation. We're just having a chat with a friend and we learn something about the friend. So knowledge has increased. About a nation in the course of reading the news, right? So we just read the news that I guess COVAX or the corona vaccine is being distributed in Ghana today. So about a nation in the course of reading the news. About a set of people as we read a book. So knowledge is accumulated over time. And we say such accumulating representations are called cognitive models. So cognitive models allow for new knowledge to be added to old knowledge. And the cognitive model might differ. So your cognitive model might differ from mine. Yours is more detailed, mine is less detailed, but we both use them routinely. Our knowledge maybe on different topics may be different, but we use them. A cognitive model might consist of knowledge about some set of entities, the characters in a story and the objects they have available to them, right? It's knowledge about some entities, knowledge about a set of properties, the size and colors of the objects, the goals of the characters, information about time and events. At what time T did character X meet character Y, and what did X know at time T? So cognitive model consists of changing knowledge and also knowledge about entities, properties, characters, information about time, and so on. A cognitive model incorporates all of these things. And now we argue that transformer plus reasoning is not cognitive. If we argue, well, let's just use the transformer, which remembers all of Romeo and Juliet, right? No problem. It knows all the text. And transformer's input to a downstream reasoning system is not a cognitive model. So we can't simply say we just put the cognitive model on top of the transformer. Why? The essence of language comprehension is to derive cognitive models from discourse, right? So that we can reason over the models we derive, and transformers just don't do that, right? So we, in the course of the conversation, we derive the cognitive model from that and not simply make a summarization like a transformer does. Predicting word classes is impressive, but prediction does not equal understanding. The beauty of transformers, of GPT-2 and BERT and so on, GPT-3 also, is that it can amazingly predict what is the next word, next phrase, next sentence, and so on in perfect coherent English, but it does not equal understanding. And we'll have, again, some more examples. All right. Now, that was all about natural language. What about our computer vision? Scene comprehension. So deriving rich cognitive models from text and videos. What about computer vision systems? Do they understand what they're observing? Deriving rich cognitive models from videos, for example. So scene comprehension aims to interpret visual scenes not only in terms of what objects are there, but how the objects relate to one another. Example, not just identifying a glass on a table, but taking note of the fact that a particular glass is on a table in a particular room. So we have a glass on a table here in this picture. It looks like it is some brown liquid, maybe some Scotch whiskey on a whiskey glass. And it's on a brown table. Looks like some bar, it looks like maybe, in a particular room. That the glass is near the edge of the table and it is supported by the table. So it is not simply saying that it's glass on a table, but there is some more that goes on here and how the objects relate to one another. Oh, this is an interesting example, combining reasoning and cognition, right? So the previous one was the scene comprehension. So this one is about combining reasoning and cognition. Let's say at 12 p.m., a child is left alone in a room with a closed cookie jar containing a cookie. At 12:05 p.m., it is observed that the jar is closed, but the cookie is nowhere to be seen. So we ask a question, what happened in between? What happened between 12 p.m. and 12:05 p.m.? Combining temporal and spatial reasoning. So there is temporal, 12 p.m. to 12:05 p.m. That is temporal reasoning. It's reasoning in time, and spatial in terms of what is observed. So we can readily infer what happened. Well, A, the child opened the jar. B, the child removed the cookie. C, the child ate the cookie. D, the child closed the jar. So one can make this inference. For bonus points, you can infer that B must have happened before both C and D. That is, the child removed the cookie before the child ate the cookie and before the child closed the jar. That's an additional inference. But also that the order of C versus D, the child ate the cookie and the child closed the jar, is unknown. That ordering is not known. So these are the kinds of inferences that one can make based on observing the two visual scenes at 12 p.m. and 12:05 p.m. So what does it take to do this kind of an inference? In conjunction with a theory of biology, you can construe the child as a container and realize that the cookie is now contained, partly digested within, having traversed from an aperture, a mouth, into yet another container, the stomach within. All right. So we need to have some kind of a theory of biology here about, eating a cookie so that the cookie disappears now, and because it's gone into the stomach of the child, right? So it is combining reasoning and cognition. Cognition is looking at these visual images. Reasoning is what kind of reasoning is needed to be able to answer these questions that a human being would be able to do that very easily. All right. So what does it take to do this? So we say AI needs cognitive models. Make these kind of inferences robustly without both internal cognitive models and mechanisms to reason over them. All right. So we need internal cognitive models and mechanisms. I think it should be with both internal cognitive models and mechanism reason over them. Without this, there is no way to reliably understand a detective story, a conversation that goes beyond small talk, or virtually any narrative of human interaction. So you need a cognitive model that was illustrated by the cookie example, that you need this for AI to understand any kind of human interaction. So the conjecture for robust intelligence, what is needed for robust intelligence, is that we need cognitive models. We cannot construct rich cognitive models in an adequate automated way without three things. So to be able to construct rich cognitive models, we need a hybrid architecture, combining both, and we need rich prior knowledge, and we need sophisticated techniques for reasoning. And then the second conjecture is that robust intelligence needs rich cognitive models. We cannot achieve robust intelligence without the capacity to induce and represent rich cognitive models. So cognitive models involve hybrid architectures, prior knowledge, techniques for reasoning, right? So these three things are needed. And so what the neurosymbolic architecture, the thinking fast, thinking slow we talked about, is some direction towards how should the hybrid architecture be, what kind of prior knowledge should be there, which is about the world at large, and then sophisticated techniques for reasoning. And here we argue that more data will not solve this. So can we argue that, just keep on feeding it more and more data? Google's Meena, which was announced in 2020, it was trained on a massive 341 gigabyte corpus, 10 times the size of what GPT-2 was trained on. We've largely talked about GPT-2. This is 10 times the size of GPT-2. Equivalent of 341,000 books, right? More than any human being would read. There is that amount of information was fed to Meena. And they wrote a blog saying, towards a conversational agent that can chat about anything. This is Meena, meet Meena. Meena can conduct conversations that are more sensible and specific than existing state-of-the-art chatbots. Right, here's a small video. Let's see if you can see this. Right. Maybe I need to share this, huh?
Does the video?
Have you ever had a conversation with Siri?
Hey Siri.
Hey Siri.
Hi Bixby.
Okay, Google.
Alexa, play my favorite song.
Yeah, Every time I have a conversation with AI technology like Siri, something always goes wrong. It makes me wonder if we'll ever get to that stage where we can have a proper, real, natural conversation with the machine. Let me introduce you to Google's new project, Meena. Hi, I'm Chris, a software developer at AI Network. Google has released a neural network-powered chatbot called Meena that they claim is better than any other chatbot out there. The secret behind Meena's conversational skills is the crazy amount of data it was trained on, about 341 gigabytes of text, or to put that in more understandable terms, 40 billion words, including millions of social media conversations. What separates Meena from other chatbots is its ability to give specific context-dependent answers. For example, if you say, "I like football," and a chatbot replies, "That's nice," the response makes sense, but is not specific. So let's try chatting with Meena. As you can see from the chat logs, Meena not only answers questions sensibly and coherently, but is even capable of cracking a joke. Next, you see a selection of topics where the user talks with Meena about movies, and the bot even expresses the desire to see these movies too. This is very human-like. Meena even tried to come up with a proper definition of philosophy. These scholarly-like attempts to answer such deep questions is much more advanced than previous state-of-the-art chatbots. In order to understand how Meena works, you need to read Google AI's recent paper, Towards a Human-like Open Domain Chatbot. Meena's main architecture is a sequence-to-sequence model with an evolved transformer. Meena was trained on 40 billion words mined and filtered from public domain social media conversations. Compared with OpenAI's self-learning language model, GPT-2, which is a neural network variant with 1.5 billion parameters, Meena is 1.7 times bigger in model capacity and was trained on 8 times more data. That means Meena's new transformer architecture, developed through an evolutionary neural architecture, searches to improve perplexity. To evaluate Meena's performance, researchers proposed a simple human evaluation metric called SSA, which stands for Sensibleness and Specificity Average. SSA considers 2 fundamental aspects of a human-like conversation, which is a full 23% higher in absolute SSA than existing state-of-the-art chatbots, such as Mitsuku, Cleverbot, and Diolo GPT, which means that it's easy to mistake Meena for a real human. Today we learned about Google's Meena. This already sounds like science fiction, and it will be difficult to reach the seamless interaction between humans and AI we all dream of someday. However, with the best AI teams continuing their amazing work on great projects like Meena, I believe these kinds of services will one day be amazing. I hope many developers will be inspired by projects like Meena to make more incredible, fun AI projects. So that's it for this week's video. Thank you for tuning in, and don't forget to click on the subscribe button. Talk to you next week for next week's weekly iNight video.
So the first question that comes out, of course, is that whenever you see machine learning or you hear about machine learning, it seems to be like this magic wand. Your boss says, put machine learning into your application. Or if you hear about startups, they put machine learning into their pitch somewhere and suddenly they become like a viable company. But what is machine learning? What is it really all about? And particularly for coders, what's machine learning all about? Actually, quick show of hands, how many of you are coders? Yeah, it's I.O. I guess pretty much all of us, right, are coders. I do talks like this all the time, and sometimes I'll ask how many people are coders, and 3 or 4 hands show up. So it's fun that we can...
Okay, I had a bit of a trouble turning off the browser. Okay, so anyway, you got the sense of what Meena is like. Okay, let's go back. Let's go back. I hope you can still see my slides, right?
No, Professor.
No? All right, so let me again share this. Okay. You can see it now, right? Okay.
Yes.
All right, let me put it on slideshow mode again, which is probably going to start all over in the beginning. So you got a sense that Meena sounds like it is absolutely amazing, right? It is at least state of the art about a year ago. Maybe it's even further along now than there. But now we're going to say, what does it mean really? Quality of Meena's conversations. like GPT-2, Meena produces prose that is both remarkably fluent and also remarkably on topic. Its best dialogues are stunning, and the paper reports that it sets a new state of the art in a new measure of sensibleness and specificity. They talked about that in the video, that it is better on that measure than so many other systems. But the same core foundation and internal cognitive model of the world is still missing. It is able to do all these impressive things, but it's not understanding. How do we say that? Meena conversation examples. Here is a link. They give, like hundreds of conversations that Meena has had with human beings. So let's look at conversation number 61. Human, what's your favorite band? Meena says, Avenged Sevenfold. I never heard of this. Anyone know? Have you heard of Avenged Sevenfold?
No.
No? Okay. All right. I guess I should look at the chat box to see what you're all saying. All right. I guess you're all as ignorant about bands as I am. Avenged Sevenfold. Right. Okay. Anyway, let's see. What's your favorite band? Avenged Sevenfold. Human. Oh, that's a good answer. What's your least favorite band? Meena says Avenged Sevenfold. Human says, oh, I thought you liked Avenged Sevenfold. Meena, yeah, that's my favorite band. So you see, even this pretty fancy Meena system is giving you very well-composed answers, but they don't necessarily make any sense. So it can't keep track of what it previously said and what is saying again and looking at the logic of what is the best and what is the least and that kind of thing here. Let's look at conversation 77. The human says, what are some of your New Year resolutions? Meena says, lose 60 pounds, learn Cantonese, learn French. Human, don't you think that's pretty far-fetched? Meena says, not really. I'm currently down 35 pounds. I can already speak Cantonese at a basic level, and I'm already learning French in school. The human says, wow, that's impressive. Meena says, I'm learning French on the side. It's really easy for me since I'm a native Cantonese speaker. What? Is it easier to learn French if you are a native Cantonese speaker? So these are examples that they've picked out. Of course, there are hundreds of examples. If you look at this particular link, I will not click on it because of all this, all the sharing issues that come up. But they picked out some of these things saying, look, this is not understanding. So evaluation of Meena. Each answer is coherent, but there is no coherence from one answer to the next. So every one of them is coherent, but not relating that to each other. Meena captures the fact that certain phrases like band names are often correlated with phrases like favorite band. So it is understanding there is some kind of correlation. When you say favorite band, okay, I got to give a band name. But there is no enduring record of Meena's preferences. So what are Meena's preferences? Which band do you like? Even for the length of a short conversation, let alone Meena permanently. But even during that conversation, it cannot keep track of what its preference is. And hence complete inconsistency. Okay, so now we talk about the role of abstract knowledge in human life, right? The importance of abstract knowledge. So that's what we're driving at. This is rather than correlation type of issues, abstract knowledge. Okay, we begin by a big philosophical statement. Without us, the world would continue to exist, right? Without human beings, the world would continue. I guess it existed during the time of dinosaurs, right? The world would continue to exist, but it would not be described, distilled, or understood, right? So the world exists, but without understanding. A bird might flap its wings. Let's say you look at a video or a real in life, see a bird flapping its wings. When a bird might flap its wings and the bird might be carried along in flight. We see it flapping its wings and it's carried along in flight. Well, there would be correlation between the two, but not a causal description. So we would just observe it, observe the world as it is, that there is a correlation between these two things. So whenever we see a bird flapping its wings, we can say next thing is it's going to fly. But not an understanding. I suppose an understanding is pretty deep here, because we'd have to talk about things like aerodynamics and thrust and things like that, right? Because a bird flight is different from an aircraft flight. With an aircraft flight, you'd have to talk about thrust and propulsion and drag and lift and things like that, right? Whereas with a bird here, talking about flapping wings and so on. In any case, we might have a correlation between the two, but not a description. Why did the bird fly? That kind of thing. And we now argue that human lives are filled with abstraction and causal description. So our lives are constantly about abstraction. Even children spend a large part of their time asking why, right? We're all familiar with children and they keep asking, but why? Why is this? Why is this? They're always trying to find out why. They want a reasoning behind it. Scientists ask such questions in order to generate theories. We also, right? Newton wanted to know why the apple fell on top of him, right? He was a scientist who was asking to generate a theory of gravitation. Our power comes from understanding and characterizing the world in the form of science, culture, and technology. So this is an essential part of human beings, and our abilities comes from understanding and characterizing the world, not just the correlation between the fact that the wings are flapping and the bird is flying. We're able to abstract as to why. So now we argue that there might be even biological support for some of this type of knowledge. This is a controversial point. Today, we argue that the neural networks, which are made of neurons, and if you recall, a neuron takes as a weighted summed input and takes that scalar value and compares it and uses an activation function like a sigmoid or a ReLU to power its output, which is then multiplied by another weight and so on. So that's a basic neuron that all of the architecture of neural networks are built up from those neurons. So neural models are homogeneous. Neurons are capable of little more than summation and integration, and often no more than a handful of pre-specified models. So the neural networks are fairly simple architectures. But if you look at the human brain, you say, is human brain just a bunch of neurons? At the macro level, the cortex is this outside layer of the human brain. The cortex alone has hundreds of anatomically and likely functional areas. So it's not just neurons, there are several hundreds of likely functional areas. Even a single dendritic compartment of a single neuron can compute the nonlinearity of XOR. So this is a little bit more than a single neuron. XOR requires a couple of neurons to be able to compute. So such a function can be done in a dendritic compartment of a single neuron has that ability. Likely that there is a diversity in neural computation, not yet been captured either in computational neuroscience or in artificial intelligence. So the argument here is, it's not just the neurons that capture correlations, which is what deep learning does, but there is also some functionalities, essential functionalities that are in the brain. But here we are speculating here. But there are structures like that, and we just haven't, unwrapped it. So now we say that robust AI resides in the intersection of learning and symbol manipulation. So we've argued that we need some kind of symbol manipulation capability, which might come from the cortex, but we have talked about what is needed. And so they're talking about two large regions here in this Venn diagram. So this part is learning. This is about symbolic operations. Learning part learns from multi-layer perceptrons trained by backprop. And here is transformer. And here are CNNs trained by backprop. These are all learning methods. Whereas the symbolic operations have ELIZA, which is the famous AI program that looked good about 50 years ago. Simply based, it's called a Rogerian psychotherapist, simply repeating what you're saying, and it looks intelligent. There was some chatbot, Mitsuku symbolic chatbot. We saw that on the Meena diagram. Psyc is the symbolic program that was done by Doug Leonard. And then there is one here called TP transformer, which is some combination of TP transformer. It's a project called TP transformer. And then there is another one here, neurosymbolic NSCL, it's called. We'll look at this one. There's a whole paper on this topic. We'll study this one, which is, so they're saying a robust AI resides in the intersection of learning and symbol manipulation. So the best one so far, it seems like it's this one, NSCL. It is neurosymbolic. NS stands for neurosymbolic. So this is what we are studying in this semester, is on this neurosymbolic method, which lies in the intersection of the two. So the need for special mechanisms is that the need for special reasoning machinery is needed for spatial, physical, psychological, temporal, causal. And current neural networks lack explicit mechanisms for these forms of reasoning. So we need different forms of reasoning: spatial, physical, psychological. Temporal means time, and then causal. Ways of representing and reasoning over such domains. So we have, this is spatial reasoning over here, and this is temporal reasoning here. And then within temporal reasoning is causal reasoning, and then there's physical reasoning and psychological reasoning. And we have ELIZA, GPT-2, BERT, multi-layer perceptron trained by backprop. All right, so these mechanisms are there, but none of them are able to do spatial reasoning. CNNs trained by backprop can do spatial reasoning. And then NSCL can do physical reasoning. All right, that seems to be in the right place here. So there are two things going on here: is neurosymbolic, and then there is also specialized mechanisms. So the proposal for a hybrid model is to achieve common sense and ultimately general intelligence. We're talking about general intelligence. Can AI perform like an ordinary human being? Develop systems to represent core frameworks of human knowledge: time, space, causality, basic knowledge of physical objects and their interactions, basic knowledge, okay, that knowledge of humans and their interactions, that's what we needed. And then embed these in an architecture that can be extended to every kind of knowledge, keeping in mind tenets of abstraction, compositionality, tracking of individuals. And reasoning that can deal with knowledge that is complex, uncertain, and incomplete, and that can freely work both top-down and bottom-up. This is the topic of graphical model, probabilistic graphical models. Reasoning that can deal with knowledge that is complex, uncertain, and incomplete, and work top-down and bottom-up. Connect these to perception, manipulation, and language. This is the kind of thing that deep learning excels in. Use these to build rich cognitive models of the world. So the proposal for a hybrid model is to develop these systems, embed them in architecture, have reasoning, connect them to perception. And the final keystone is the next slide, is keystone for hybrid model. Construct human-inspired learning system that uses all knowledge and cognitive abilities that the AI has. So the main step is for this kind of a model which incorporates perception and reasoning is that it uses all kinds of knowledge, incorporate what it learns into its prior knowledge. Like a child voraciously learns from every possible source of information, interacting with the world, interacting with people, reading, watching videos, even being explicitly taught. Put all that together to get to deep understanding, right? If you Google what is a hybrid model, all it comes up with is these cars that have both a battery that can be charged with high household electricity and a fuel tank that can be filled at a gas station, and it has got an engine that is driven by this fuel tank, and then we got a battery that drives the motor here, right? So anyway, that's a hybrid model, but I guess it illustrates the point. A hybrid model has got one of this is the old way, this is the symbolic way, I suppose, and there is a new way, this is the deep learning approach, and together to make progress. Seeing the whole elephant. Deep learning shows much can be learned from massive data, right? Learn, gigabytes of, use gigabytes of text, 314,000 books and so on. Co-occurrence statistics may be mere shadows of robust knowledge, but there are lots of shadows. Maybe we can put those shadows to use, knowing both their strengths and their limitations. So deep learning says much can be learned from massive data. That's one part. Psych shows the potential power of sophisticated reasoning in the presence of rich knowledge bases and rich cognitive models. Even if on its own, it is not capable of deriving these models directly from language or perceptual inputs. So we got deep learning on one side, psych in the middle, and then this one, NSCL, it's a paper that we'll study. It's a 2-year-old paper. Shows that symbol manipulation and deep learning can be integrated into a seamless whole. We'll take a look at this as how they did it. Not yet at scale. It can both perceive and reason. So that is the model we need to go towards. All right, we come to the summary of this idea called robust intelligence. We described what is robust intelligence as not failing unexpectedly. Robust intelligence needs cognitive models. More data, simply adding more data is insufficient, as shown by Google Meena. Cognitive models incorporate reasoning with models of time, space, and causality. And hybrid models should integrate powers of deep learning and symbolic reasoning using seamless architectures. Okay, that's the end of our robust intelligence segment. And if you have any questions on robust intelligence, we can discuss this now before we close the recording and go to your individual projects. Okay, so we will stop the recording now.